Okay, good evening, everyone. We're going to start the webcast now. The topic of today is novel workflow using AnyBody modeling system and mechanical finder to do finite element analysis of osteoarthritic gait. So the program for today is that I'm going to give you a very brief introduction into the AnyBody modeling system. And after this, I will give the word to our guest speaker, Daisuke Tawara. He is an associate professor at the Department of Mechanical and Systems Engineering at the Faculty of Science and Technology in Ryukoku University in Japan. And my name is Pavel Galibarov, and I will be the host for today. After the presentation by our guest, I will say a few final words, and after this we will have a very brief question and answers session. So let me start by introducing you the AnyBody modeling system. So many of you already know what it is, but normally when we speak about the AnyBody modeling system, we speak about two products. So one of them is called the AnyBody modeling system, and the second one is the AnyBody managed model repository. So the first one is the modeling environment, or in other words, it's a modeling engine which solves all kinds of equations in the background, and we also have an associated repository of models that can be used to build your models from already ready templates, so you don't need to assemble model from scratch. Okay, so the AnyBody modeling system can be applied in many fields. Whenever the problem is human-centered, the AnyBody modeling system can be applied. And quite traditionally, gait analysis can use a system like AnyBody. It can also be used for product design optimization for all kinds of sports products or consumer products. It can be used for assessing the ergonomics of a workplace or the product again. It can be used for medical device tasks, for surgical planning and outcome evaluations. And we could also look into boundary conditions for finite element analysis when this is needed. And this is going to be the topic of today. So AnyBody modeling system is an inverse dynamic system, and typically to construct a problem, we do the following. So we take a template body model that comes directly from our repository, and we prescribe certain motion and some external forces. For example, it can be either some synthetic motion or it can be motion capture recorded data, and we would apply external forces such as contacts with the environment, if known, or, for example, force plate data. Additionally, we would put some sort of environment objects into that, whether this is a consumer product or a medical device or an exoskeleton or something like that. Once the problem is constructed, so we perform the inverse dynamics analysis, where we compute we solve the muscle recruitment problem where all muscle forces and joint reaction forces are found, and that gives us the final output. And an example of this output you can see on the right. It's a gait analysis of a human wearing some sort of assistive device, and you can see this assistive device being engaged around the knee joint. And the AnyBody modeling system computes all kinds of kinematic parameters, muscle forces, and joint forces, and so on, all kinds of internal body loads that are not that are quite difficult to measure otherwise. And once we computed all these loads, we could send them further to finite element tools to do structural analysis of either a bone or a medical device like a fracture fixation plate or something like that. And this could, of course, then be wrapped into some sort of design optimization loop where all the systems will be called one after one in order to achieve some sort of optimal design. And as a part of this process, of course, we show that finite element analysis can be applied, and we would like to add some motivation to do multiscale simulation using the AnyBody modeling system and finite element packages. So when we do structural analysis of, let's say, medical devices, we rarely know the internal loads in the body, and we either rely on available publications which provide us with certain values, or we look at the standards, like, for example, a 4-point bending ASTM load case. But in reality, the loading patterns can be quite different, and we are also experiencing quite different loads during daily activities. So there is an uncertainty how the actual loading scenario looks like. And because of that, we think a musculoskeletal modeling combined with finite element can be an interesting strategy to answer this question. Secondly, in case of bone remodeling applications, the detail that musculoskeletal models provide in terms of internal loads, they are very important because the bone remodeling is governed by different levels of strain and stress in the bones. So whenever there is a large error in the strain or stress, we basically get a slightly different tissue, which is not very optimal. As well as that, whenever we try to do contact modeling, and for example, we want to analyze a novel knee implant, and we would like to understand how this changes the pressure patterns inside of the knee joint, a finite element model can be constructed using data from AnyBody simulation as well, or musculoskeletal simulation in general. And that could give us more precise information about the actual loads in the knee joint. And on this note, I would like to give the word to our presenter, Daisuke Tawara. He is going to talk about the novel workflow to combine AnyBody modeling system with mechanical finder. Please give me a second. I will make him the presenter.
Okay, hello everyone. Thank you, Pavel, for a kind introduction. Today I'd like to talk about new finite element analysis flow using the AnyBody modeling system and a mechanical finder. That is a popular software made in Japan to analyze osteoarthritic gait. My name is Daisuke Tawara from Ryukoku University in Japan. But in this year, I've been staying in Aalborg University, Denmark, as a guest researcher. So let me start with the introduction to hip osteoarthritis. Hip osteoarthritis is a disease which deforms the femur and hip cup due to friction of articular cartilage, and it leads to abnormal gait due to a decrease of muscle forces and leg length inequality. Orthopedic doctors often treat it with a total hip arthroplasty, THA, to improve it, but this disease and the THA are closely related to forces occurring in muscle and bones in gait motion. So to assess and predict the relationship between the seriousness and the abnormal gait, recovery of gait motion after THA, determination of THA position, and bone remodeling and an implant subject to specific stress analysis is necessary. On the other hand, to define boundary conditions for finite element models are significant challenges. We also have FE models such as a single vertebra, pelvis and femur, and a large-scale spinal instrumentation including other projects. But the problem is boundary conditions are simple. So we'd like to define muscle forces and joint reaction forces based on the musculoskeletal simulation using the AnyBody modeling system and apply them to FE models. So our aims in this project are to construct a computational flow of FEA using AnyBody modeling system and a finite element system. That is mechanical finder. I'd like to introduce it later. Development of the subject-specific musculoskeletal model for gait motion of osteoarthritis patients, and to assess gait restoration after surgery, and detect important muscles to improve abnormal gait treatment strategy. So let me introduce Mechanical Finder first. Mechanical Finder is a famous software made in Japan, which is specialized for CT image-based modeling and FEA of bone, and is widely used, especially by medical researchers and engineering researchers. In the Mechanical Finder, we can make a FE model based on CT images easily by a semi-automatic segmentation procedure, reflect heterogeneous material properties, and analyze stress distribution using a static FEA or nonlinear fracture FEA techniques. All functions are in one package. Easy reflection of material property distribution of bone is one of the advantageous features of the Mechanical Finder. Young's modulus of bone can be calculated based on bone density by defining it for an element one by one in this way. So heterogeneous material properties reflecting the patient's degree of seriousness can be modeled. It has been known that stress distribution changes depending on definition of material property distribution of bone. These definition of material property distribution of bone as a homogeneous one, two-layered one, such as a cortical and a cancellous bone, and an inhomogeneous one. You can see the difference of the stress distribution depending on the definition of material property of bone. So we'd like to use this function of the Mechanical Finder. Some papers reported validation of the nonlinear fracture FEA technique in the Mechanical Finder using the experimental caliber test of a femur and a vertebra. These graphs show the relationship between the measured yield load or fractured load and calculated ones. They confirmed positive correlations and validated the efficiency of the nonlinear FES. So we think the nonlinear FE technique in the Mechanical Finder was valid. Here are some examples of demonstrations by the Mechanical Finder. For example, you can reflect the heterogeneous Young's modulus distribution of bone to a single vertebra model, and applied loading condition increasingly, you can analyze the fracture in this way. And this example of analysis of screw pulling out during biting and with spinal instrumentation. Okay, so FE models made by Mechanical Finder look nice, but we need boundary conditions, and we want to apply muscle forces to the FE model from AnyBody modeling system. So towards the link between the AnyBody and the Mechanical Finder, the provider of the Mechanical Finder and our team had discussions. And finally, the provider made a data converter, which is called Convert AnyBody. But still, it is under the development. The current version of the converter can convert muscle forces data exported from AnyBody to mechanical finder format, but only for one-time step of the motion. And it searches for the nearest node on FE model for each muscle point. It is a good point, but the problem is mechanical finder only accepts the top 20 loading conditions due to the design of the graphical user interface under the circumstances. But it can also export all muscle forces from AnyBody as text data. So we'd like to use this data. So we will use other software in addition to the mechanical finder for our computational framework. We have mechanical finder, FEMAP Nastran, which is a general FEA pre-post processor and solver, and front ISTR, which is a large-scale FEA solver on parallel PC cluster, open free code, and made by University of Tokyo, Japan. These are the advantages and the disadvantages of the software. The advantages of the mechanical finder are easy segmentation and reflection of heterogeneous Young's modulus, but it only accepts the top 20 loading conditions. FEMAP is a function-rich pre-post processor, but FEA with heterogeneous material properties takes a long time or sometimes is impossible. Front ISTR can perform a large-scale FEA with heterogeneous material properties, but pre-post processors are a little bit poorer than commercial code. So the question is, how do we link these software packages and AnyBody modeling system? So this is our current computational framework. These are the mechanical finder, AnyBody, FEMAP, and front ISTR. We developed 4 data converters which were displayed in blue color. FEMAP is used to visualize the boundary conditions, and front ISTR is used for large-scale FEA. So if you prepare CT images and C3D file, that is the motion capture data from the patient, it can be used to make a FE model on the mechanical finder, impose the constructed shape of bone to AnyBody through the morphing and the scaling techniques, and analyze muscle forces and joint reaction forces. Then through our converter, the nodes on a FE model to apply force for all time steps can be searched. And also boundary conditions can be visualized on the FEMAP. In addition, using the mesh data of a finite element model and heterogeneous material properties file from the mechanical finder and boundary conditions file from the AnyBody, you can perform a large-scale FEA and visualize the result on a ParaView, which is also a free software. This is our current framework. So using this framework, we performed gait analysis and FEA of a hip osteoarthritis patient. Motion capture data and ground reaction forces using force plates were collected, and musculoskeletal simulation was performed on the AnyBody. As you know, using the optimization technique, the joint reaction forces and muscle forces can be calculated on the AnyBody modeling system. In this case, the analysis target is the gait motion of a Japanese female, which suffers in the left femur before THA, 3 months after THA, and 1 year after THA. First, a FE model of the left femur was made based on CT images before THA on the mechanical finder. And this is a heterogeneous Young's modulus distribution. Then the right femur was also made by the mirroring technique on the mechanical finder. Then left and right femurs were imported to the AnyBody through the morphing technique. Green and red ones are imported shape of bone of the patient. As an analysis example, we focused on the one gait cycle, especially the 10% time point where the right foot left the ground, and the 60% time point where the left foot left the ground. As you see, the patient has a symmetric gait posture before THA. This graph shows the relationship between the hip joint reaction forces and the time. Each color means the joint reaction forces in the inferior, lateral, and anterior directions for the right and left femurs. As you can see, the magnitude of the hip joint reaction forces in the inferior direction between the right and the left femur were different prominently. This slide shows visualization of boundary conditions on the FE model before THA at the 10% time point and the 60% time point. For finite element analysis, we fixed some nose on the knee. If this subject was healthy, symmetry boundary conditions can be obtained. But as you can see, the boundary conditions between the left and right femurs were different. Especially joint reaction forces of the hip and the knee were different. Under the application of these boundary conditions, we performed finite element analysis. This slide shows the stress distribution before THA. As you can see, the stress distribution between the left and right femur were different due to the difference of boundary conditions. And here are one of the examples of the distribution of stress and the Young's modulus. As you can see, distribution of stress and the Young's modulus were similar, meaning that stress propagates the area which has higher stiffness in bone. So the modeling of the heterogeneous Young's modulus distribution by the mechanical finder is useful and important. So now we have been trying to analyze walking postures with the same patient before and after THA. Here, display of muscles was customized to emphasize a muscle which has higher muscle force. Actually, we haven't modeled the shape of THA yet, but you can see that asymmetry gait posture before THA seemed to be improved 1 year after THA, even only comparing gait postures. This slide shows the change in hip joint reaction forces. These are the hip joint reaction forces before THA, 3 months after THA, and 1 year after THA. As you can see, the magnitude of the hip joint reaction forces in the inferior direction and the time which the force were acted were different before THA. 3 months after THA, it still had asymmetry, but became became a balanced state 1 year after THA. I'll show you the change in stress distribution and boundary conditions. These are before THA again. As you can see, especially joint reaction forces of the hip and the knee were different. And this slide shows the 3 months after THA. Joint reaction forces slightly improved. And this 1 year after THA. Okay, this is a whole picture with the change in stress distribution. As you see, the unequal stress distribution before THA became the balanced distribution 1 year after THA. Interestingly, the stress distribution has asymmetry, still asymmetry 3 months after THA. Moving on to the next slide, you can see the change in stress distribution quantitatively. Here, we focused on the data before THA and 1 year after THA. This graph shows the histogram of stress in the model of the left and right femurs before THA and 1 year after THA. You can find the gap between the models before THA, but it became almost the same 1 year after THA. And the middle graph shows the difference of stress distribution between the left and the right femur. You can see that the difference became smaller 1 year after THA. Then we tried to visualize the difference of boundary conditions between before and after THA for the left femur. These are the boundary conditions before THA and 1 year after THA again. There are difference for all boundary conditions and top 10 boundary conditions in it. And here's a list of the top 10 boundary conditions. Number 1 and 2 are joint reaction forces, and other boundary conditions are all muscle forces. And these for the right femur. The top 10 boundary conditions are all muscle forces, not including joint reaction forces. Moving on to the next slide, you can see the top 10 muscles which changed significantly displayed in pink. These are the posture and muscles at the 10% time point and 60% time point. Interestingly, the top 10 muscles which changed significantly were different between the left and the right femurs. We think such a display is easy to understand important muscles to improve abnormal gait, and it can also provide useful information for the treatment strategy of doctors. This slide shows one of the examples of the quantitative comparison of muscles which changed significantly. The blue one is before THA, the orange one is 1 year after THA. Notably, you can find the increase of muscle forces. And this slide shows the quantitative display of differences of the boundary conditions in descending order for the right and left femur. As you can see, the difference of boundary conditions and their tendency are symmetry between the right and left femur. Improvement of the joint reaction forces was significant and seems to be dominant in the left femur, while more muscle forces changed in the right femur. Okay, let me move on to the discussion slide. FEA flow still seems to be complicated, but it is the best under the circumstances. Improvement of the FEA flow for a direct link from AnyBody to mechanical finder will be continued. Actually, the implant inserted in the femur should be modeled, but the approach to assess changing gait posture and stress distribution could be useful to evaluate gait restoration. And display of muscle forces which changed significantly can suggest important muscles to improve gait posture. It can lead to understand the mechanism of abnormal gait and approach of treatment strategy. Let me summarize my talk. Basic FEA flow for gait analysis using AnyBody and mechanical finder was constructed, and stress analysis of femur under the application of boundary conditions while walking was performed. Approach to assess the relationship between changing gait posture and stress distribution can be useful for clinical treatment for abnormal gait of hip osteoarthritis. And this is our future vision. We have been collecting motion capture data of patients from 50 to 100 patients before THA and 1 year after THA at target. Then we are going to analyze stress distribution of the femur using our workflow of musculoskeletal simulation and FEA, and also apply them to statistical prediction. We think it could be lead to an indication to the treatment strategy based on understanding important factors for improvement of abnormal gait and prediction of improvement of abnormal gait after THA at the point before THA. Finally, I'd like to thank JSPS for the research grant and our collaborators, and thank you for your attention.
Okay, thank you very much for a very nice presentation. I'm going to say a few words, and please submit all your questions right now, and we will review them in a few seconds. But what I would like to say is that this webinar will be recorded, and if you want to watch it again, it's going to be available on our YouTube channel, where you can find previous webinars and some interesting videos. We also have please also visit our website, where you can find a lot of information about different applications of AnyBody modeling system. You can also find all kinds of different events and dates and so on. And you could also visit our special website that is called anyscript.org. And this is AnyScript community website where we share information with some of our customers. So if you're interested in certain questions and you're a user of AnyBody, this is a very nice forum for you.